Right, we're going to continue today with calculating the force on a particular charge if I have more than one charge involved in the scenario. And so today we're going to be working example 13.2, the second part of that, which actually starts on page 436 in your text. It says 3 charges are arranged at the vertices of a 45, 45, 90 right triangle. And it wants to know what the electrostatic instantaneous force acting on the 6 Coulomb charge is. Okay, so I have copied that diagram up here. You should easily recognize that if I have a 45, 45 right triangle, then the 2 legs of that triangle are also going to be congruent to one another, distance of 0.34 meters. Hypotenuse over here. We have constructed just a horizontal here so that these 2 are in vertical alignment with one another, and then here's the horizontal. So we will need that in order to get all of our trigonometry in the right spot there. We are looking at this particular charge up here. This is the one we're trying to calculate the force on. So I'm going to calculate the force first with this one and then with this charge. And just to kind of simplify my notation here, I'm going to call this charge A and I'm going to call that charge B. So for charge A, your force is going to be, again, we're going to be using Coulomb's law here. So it's going to be 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. And thankfully this time the charges are just in Coulomb, so I don't have to worry about adding that times 10 to the minus 3. So I have a 6.0 Coulomb charge and I have a 4.0 Coulomb charge, and the distance between them is 0.34 meters, and that's going to be squared. So that is going to give me a final answer of 1.9 times 10 to the 12th newtons. Okay, now that's a nice number, but I have to figure out exactly what it means. So if I look at the 2 charges here, this is a positive charge and this is a positive charge, right? So if they're both positive, they are going to repel each other. So I know that this is a repulsive force. So which direction does that mean on my diagram that it's going to be acting? Well, it's going to be they're going to be pushing away from each other. So this charge is going to have this force acting on it this direction. So this is going to be 1.9 times 10 to the 12th newtons up on that side of it up there. Okay? So it's important to figure out which direction that's acting and to actually go ahead and put that into your diagram. Now we're going to look at charge B, which is this one over here. What charge or what effect does that have on this charge? So the force again is K. And then the first charge I'm looking at is the 6 Coulomb charge. And the second charge is a 2 Coulomb charge. And there is 0.48 meters between them. Okay, so when I crunch all those numbers, I end up with 4.7 times 10 to the 11th newtons. What about these 2? This is positive and this is negative. So what that means is that this is actually an attractive force in place of a repulsive force. So that means that these 2 charges are going to be drawn, I'm going to use that color, are going to be drawn towards each other. So this particular charge, since it is attractive, these 2 are going to be drawn toward each other. So that means this one is going to go right along that line here, and it's going to be 4.7 times 10 to the 11th newtons. Okay, so now that I have my drawing updated with which direction these are going to be going, now's where I have to come in and do the trig. Now, these problems are worked exactly the same way as the problems that we worked back in Module 3. So if you're really rusty on that and you need some review, that would be the place to go back and look, is back in Module 3 when we did these types of trigonometric calculations. So I'm going to go ahead and set it up just like I did before. I have an x component and I have a y component. So when I look at charge A, the force resulting from charge A is 1.9 times 10 to the 12th. So it's going to be 1.9 times 10 to the 12th newtons. And which direction is it going? Well, remember that we said that this is always 0 and we always go counterclockwise. So this is making a 90-degree angle. So that's the angle that I have to use. We also said that the horizontal component, we have to multiply by the cosine of that angle. So here I'm going to multiply by the cosine of 90 degrees. Do I have the right number of significant figures on there? Yes, it was to the 10th place. Okay, so the cosine of 90 degrees, well, the cosine of 90 degrees is 0, so this is going to be 0 for the x component. That should make sense because this is completely straight up. There is no horizontal, or the horizontal component of that is 0. I can't say there is no horizontal component. There is, but the horizontal component is 0. It's all vertical. So similarly, I'll need to do the same thing for the y component. I'll have 1.9 times 10 to the 12th newtons, and I'll take that times the sine of 90 degrees, which is 1, and so that will give me 1.9 times 10 to the 12th newtons here. Okay, again, all of the forces going completely in a vertical fashion. Now I need to do the same thing with force B. So force B was 4.7 times 10 to the 11th newtons. Now, what angle am I going to be using here? Well, this vector is pointing down this direction, and it's 45 degrees from the horizontal. But remember, I have to start here and go around this direction. So I have 90, 180, 270, plus another 45, which is going to give me 315 degrees. Okay, so I need the cosine of 315 degrees, and that will give me 3.3 times 10 to the 11th newtons. And then I'll need to do the same thing for the y component. I've got 4.7 times 10 to the 11th newtons times the sine of 315 degrees. And that number comes out to be a negative 3.3 times 10 to the 11th newtons. Okay, so all this should look really familiar. It's the same kind of thing we did back in Module 3 when we were looking at whether we were looking at velocity vectors or we were looking at force vectors. Okay, here we're looking at force vectors, but we have to keep in mind the angle that they're acting at. So now that I have the x components, I can add those x components together. So this obviously is 3.3 times 10 to the 11th newtons. If I add these two together, that's going to give me 1.6 times 10 to the 12th newtons. And both of these numbers are positive. And if you would go back and actually add these graphically, this is times 10 to the 12th, this is times 10 to the 11th. So when you think about that, it does end up that this number is much bigger than this one. So I've got one vector going up this way, and then my green vector is going down this way, but it's not very big in comparison. So it's going to be about like that. So once I do that, then that vector is going to come up there like that when I actually add them two together if I did it graphically. Okay, so when I get my final answer, I should be in that general neighborhood. Okay, so what do we do with this now? Well, if you recall, The only way to get the magnitude of the vector is to use the Pythagorean theorem. So I then have to do side squared plus side squared. So I'm going to have to take the square root of 3.3 times 10 to the 11th newtons, the quantity squared, plus 1.6 times 10 to the 12th newtons, that quantity squared, and then take the whole, take the square root of that whole thing, which will give me 1.6 times 10 to the 12th newtons. Okay, so this is my final value of force. Now, what angle is it at? Well, again, in order to find that angle, I've got to use an inverse tangent. So it's going to be, yeah, that's right, tangent to the -1 of theta is going to be equal to, actually, I didn't really write that correctly. Let's try that again. So theta is going to be equal to tangent to the -1 of the y component, which is 1.6 times 10 to the 12th newtons, over the x component, 3.3 times 10 to the 11th newtons, and the tangent on that ends up being 78 degrees. Now, you'll remember that depending on which quadrant your vector ends up in, you sometimes have to do something to the degree measurement that you get from that. And if you recall, this diagram was, way back in Module 3. If your vector is here, then you have to do nothing to it. If your vector is in the second or the third quadrant, you have to add 180 degrees to it. And if your vector ends up down in this fourth quadrant, you have to add 360 degrees to it. Okay, well, we've already said that this is going to be in the first quadrant. If you didn't draw the vector diagram to figure that out, you would still know that it was in the first quadrant because the x component and the y component were both positive. So x is positive, y is positive, that puts you up in this quadrant up here. So even if you don't actually draw the vectors, or if, sometimes those powers can kind of confuse you and you're like, well, which one's even really bigger? But the fact that the x component is positive and the y component is positive, that will tell you that it's going to end up in this quadrant. If your x component was negative and y component was positive, that puts you up in the second quadrant, etc. Okay, so you can look at the signs on that to be able to tell. So our final answer then is going to be 1.6 times 10 to the 12th newtons at 78 degrees. So there is our final answer for that problem. All right, so you're going to have the opportunity to work a couple of those yourself today. Again, should be reviewed because it's the same type of thing that we did back in Module 3. Really the only difference is that you've got to use Coulomb's law to calculate the magnitude of the force to start with, and then you're going to have to say, okay, is it attractive or is it repulsive, and which way is that going to point? So you have to think about all those things before you start doing all the trig.